This is a video for my Exam 4 review in my Calculus 1 class. So let's start off with problem 1. Suppose we have the integral of cosine theta divided by 1 plus sine of theta d theta. So I'm going to let u equal 1 plus sine of theta. So notice how the derivative of the denominator is the numerator. So in other words, the derivative of 1 plus sine of theta is equal to cosine theta. So du is cosine theta d theta. And so we can write this as the integral of 1 over u du. But this is equal to natural log of the absolute value of u plus c. But u is 1 plus sine of theta. So this is natural log of the absolute value of 1 plus sine of theta plus c. And that's how you do problem number 1. So let's take a look at problem number 2. Suppose we have the integral of cosine cubed theta times sine of theta d theta. So this again is another u substitution problem. And I'm going to let u equal cosine theta. Du is negative sine theta d theta. And so I want to solve for sine theta d theta. So if I solve for sine theta d theta, I get negative du. And so this is equal to negative the integral. Wherever I see a cosine theta, I'm going to replace it with u. So I get u raised to the third power du. So this is negative 1/4 u to the 4th plus c. But remember, u equals cosine theta. And so this is negative 1/4 cosine to the 4th theta plus c. And that's how you do problem number 2. Let's take a look at problem 3. Suppose we have the integral of e to the negative 3r dr. Now, here, I'm going to let u equal negative 3r. du is negative 3 dr. Solving for dr, I get dr, dividing both sides by negative 3, I get negative 1/3 du, or negative du over 3. They're both okay. So I'm going to take a negative 1/3 out in front of the integral, so I get negative 1/3 the integral of e to the u du. So this is negative 1/3 e to the u plus c. But remember, u is negative 3r. So I get negative 1/3 e to the negative 3r plus c. And that's how we do problem number 3. Let's take a look at problem number 4. So on problem number 4, we have the integral of sine of 1 over x divided by x squared dx. Now, one thing you could do if this helps is rewrite this integral. And I would rewrite it as follows. I would write it as sine of 1 over x times 1 over x squared dx. Now, why would I do that? Because if I let u equal 1 over x, I know that the derivative is negative 1 over x squared. And that's what I want, because the only thing missing over here is that negative sign. And we could easily take care of that. So, in other words, I'm going to let u equal 1 over x. And so du is negative 1 over x squared dx. So solving for 1 over x squared dx, I get 1 over x squared dx is equal to negative du. And so this is negative the integral of sine of u du. Right? So negative the integral of sine of u du is equal to negative of negative cosine u plus c, right? But u is equal to 1 over x. And so this is equal to cosine of 1 over x plus c. And that's how you do problem number 4. So, and with that, we're going to take a look at problem number 5. So, on problem number 5, we have the integral of natural log of x raised to the second divided by x dx. Now, again, just like in number 4, if it's too confusing, we can write it this way. We can say natural log of x raised to the second times 1 over x dx. Because I just know that the derivative of natural log of x is 1 over x, and it can help me in identifying my u. So I'm going to let u equal natural log of x. Du is 1 over x dx. And so the natural log of x squared divided by x dx is the integral of u squared du. But this is 1/3 u cubed plus c, right? But remember, u is ln x. So therefore, the integral of natural log of x raised to the second divided by x dx is 1/3 times natural log of x raised to the third plus c. And that's how you do problem number 5. Let's take a look at 6. Suppose we have the integral of sine of x times sine of cosine x dx. Now, when I look at a problem like that, I just happen to notice that if I take the derivative of this inside function here, I get negative sine x. And I notice that I'm pretty close there. So that would be a suitable choice for u. So I typically go for the inside function when trying to identify u. So I'm going to let u equal cosine x. Du is negative sine of x dx. So sine x dx is negative du. And so this is negative the integral of sine of u du. So come up here. Negative the integral of sine of u du is equal to cosine u plus c. But remember, u is cosine x. And so this is cosine of cosine x plus c. And that's how you do problem number 6. So let's take a look at problem 7. Suppose we have the integral of secant squared theta times tangent cubed theta d theta. Now, remember, the derivative of tangent theta is secant squared theta, okay? So I'm going to write it in this form, or in this format, if you will. So I could write this as tangent cubed theta, okay, times secant squared theta d theta. And what I'm going to do is let u equal tangent theta. And my du is secant squared theta d theta. That's important. And so this is the integral of u cubed du. So what would the answer be? It's 1/4 u to the 4th plus c. Now, you get into here, I'm pretty happy, right? But remember, you have to transform that integral back in terms of theta. So I'm going to let u equal tangent theta. So when I go to plug that back in, I get 1/4 tangent to the 4th theta plus c. And that right there is problem number 7. Let's take a look at problem number 8. On problem number 8, we got the following. I want to go over this one. X times the square root of x plus 2 dx. And this is something I like to teach my Calculus 2 students. If at all possible, try to get rid of the radical. Okay? And so what I'm going to do is let u equal the square root of x plus 2. To get rid of that radical, we need to square both sides. And so u squared is equal to x plus 2. But I need to figure out what x is. So x is u squared minus 2. dx is 2u du. Now we're ready to stuff in. Wherever I see an x, I'm going to put in u squared minus 2. Wherever I see a square root of x plus 2, I put in u. And then dx right here is 2u du. So I'm going to put in 2u du. And that's what it's supposed to look like. And so 2u times u is 2u squared. So I get 2u squared times u squared minus 2 du. And we could do that, right? Because we're going to distribute to each term within the parentheses. And so this is the integral of 2u to the 4th minus 4u squared du. And I'm just about done. So this is, if we look back, if we integrate the first term with respect to u, we get 2/5 u to the 5th. back here. 2/5 u to the 5th minus. If we integrate the second term, we get 4/3 u cubed. And then we just add our trusty c. But remember u is square root of x plus 2. Okay? And so this is 2/5. And oh, by the way, this is x plus 2 to the 1/2. So this is x plus 2 to the 5/2 minus 4/3 times x plus 2 to the 3/2 plus c. And that's how you do problem number 8. Problem number 9. Suppose we had the integral of e to the arc sine x divided by square root of 1 minus x squared dx. But we can write this in a different way. We can write this as e to the arc sine x times 1 over the square root of 1 minus x squared dx. So what we're going to do is let u equal arc sine x. Du is 1 over the square root of 1 minus x squared dx. So I just happen to know when I look at arc sine x and take its derivative, I get 1 over the square root of 1 minus x squared. Also, arc sine x is that inside function that I always desperately look for. And so this is the integral of e to the u du. And this is e to the u plus c. But u is arc sine x, right? That's what we got over here. And so this is e to the arc sine x plus c. That was number 9. Let's take a look at number 10. On problem number 10, we have the integral of secant squared theta divided by tangent theta d theta. This one's good. So I'm going to let u equal tangent theta. Du is secant squared of theta d theta. So this is the integral of 1 over u du. What's the answer? Well, it's natural log of the absolute value of u plus c. But u is tangent theta. So I get natural log of the absolute value of tangent theta plus some constant c. So that's problem 10. And that's a good stopping point. That's actually not bad at all. So we did the first 10 problems off the exam 4 review. Please let me know if you have any questions, and I will be posting more integrals. So thank you very much.